I'd like to introduce Lukas Fittl for a talk on the monitoring Postgres.
All right. Can everybody hear me fine this way? Cool. Awesome. All right. I'm going to talk about a map for monitoring Postgres. So I've talked about Postgres monitoring for a while. This is a new talk for me, so if something is confusing, feel free to let me know at the end, or if it's really confusing, feel free to try to interrupt me as well. All right, why am I talking about monitoring? So a couple of logos up for you here to kind of see what I'm doing. So right now I am a member of the Azure Database for Postgres team. So Microsoft right now has a big investment in Postgres. Feel free to talk to me or other folks at the booth about that later. I used to work at Citus Data, which got acquired by Microsoft. We operate a kind of database as a service, similar to RDS, which gave me personally also a lot of insight into different workloads from an operator perspective and provider perspective. And then last but not least, I run a service called PgAnalyze, which I've been doing since 2012, so almost 8 years now, which is essentially a hosted Postgres monitoring service. So imagine it like Datadog, but focused on Postgres. And none of the things that I'm showing require you to use any of these things. Like you don't need to use PgAnalyze, you don't need to use Azure, but both Azure and PgAnalyze offer you kind of some of this functionality built in, but all of what I'm showing is kind of built into Postgres itself. All right, so I sat down and I was like, okay, there's a lot of metrics, and this is actually post-its, and there was actually 100 post-its, a little bit over 100 post-its on what could we measure about Postgres, right? Like if we look at Postgres itself, and if we look at the system that Postgres is running in, what are the things that we could measure? And that gets tedious pretty quickly. And so this talk is an attempt to try to, clarify it a bit and like define a new structure, at least for myself, and hopefully useful for you. So I kind of, I like board games. Quick board game tip: early year of Terraforming Mars is a great game. This here is from Settlers of Catan, really simple map. So I set out and said, can we draw a map? And if I was good at illustration, I would actually, draw you one of these fancy maps where it said, this is the meadow of extensions or something. But, I'm not good at illustrations. And so I kind of took a simplified version here. And so we'll kind of talk through, each of these tiles represents something to learn about Postgres monitoring. And we won't talk about everything because it's, going to take forever. But we'll talk about a few things that I found useful over the years. Also, each slide is kind of one of these 4 categories, and each kind of topic that I'm talking about has one of these 4 topics. So either it's historic metrics, right? So it's things that we can look at in Postgres that we usually want to measure over time, that are usually in a table in Postgres that we can kind of get data from. Then there's current activity. PgStat activity in Postgres is the best example. It tells us what's happening right now. Then we have logs. So logs, essentially, Postgres log is very useful. It's a completely separate system kind of from the metrics in the statistics tables. But oftentimes we need to look at both the statistics tables and the logs. And then last but not least, I'm trying to give you a few kind of helpful tuning actions, right? So like if you're looking at a certain thing and you're like, okay, what does this mean? Ideally, there's a few hints at what you could do to optimize. All right, let's start over here on the right side of the map. So let's look at query workloads. How many of you are familiar with PgStat statements? Okay, so about half the room. So that's good. So I'll try to repeat the basics of PgStat statements. I won't go into too much details on it today, just kind of the overview of why it's important. So you could follow these steps on how to enable PgStat statements. You can also look it up online. It's an extension for Postgres. It's part of contrib though, so that means it's kind of shipped together with Postgres. It's released together with Postgres. It's kind of semi-official, which means that the good thing is these days it's enabled on most cloud platforms. So Azure Database enables it by default. Google Cloud SQL enables it by default. RDS enables it by default since Postgres 11. Heroku Postgres has always enabled it by default, and Citus Cloud, the service we used to run, also enabled it by default. So it kind of gives you a good idea of what quality it has. It has a few gotchas sometimes, but it's very good extension. It's very useful. Essentially what it does is it tells you what queries are running on a database, right? So here we see kind of a query has a particular user ID, particular database ID, and then it has the query text. And it doesn't have the actual query text, it has kind of a normalized version of that. Then it also tells you about how many calls happened and how long all these calls took, right? So the simplest thing we can do, we kind of divide the total time through the calls, and then we know what's the average runtime for each query. And that's really one of the core features. Even if you just have that, it's already very useful because it can tell you what happened in your database, right? Like what was the query workload. And then oftentimes, if you're new to database, that's an easy thing to run. Now, the other nice thing is since Postgres 9.5 and then also I think 9.6 added some of this, you can not just measure the average time, but you can actually measure kind of the max time, and you can use then kind of the standard deviation here, assuming a normalized distribution, to kind of calculate the percentiles, and you can also kind of have all of that per query. So it's really useful to understand not just how slow is a query on average. Like in this case, right, this query took about like mean runtime of about 100 milliseconds, but sometimes it actually takes 900 milliseconds, which to an application that's waiting on that, to an end user that's waiting for a page to load, is a significant difference. All right, let's talk about slow queries. So oftentimes when people think we talk about query statistics, especially if they come from MySQL, they think of the slow query log. And Postgres also has a slow query log, right? You can enable a setting called log min duration statement, which tells you kind of every time a query has happened, like once it finished executing, that exceeded a certain threshold. Right, so in this case, if we set it to 1,000 milliseconds, that means anything that runs longer than 1,000 milliseconds will get logged to the log file. And you can see here's the actual query details, right? So we can see it's a parameterized query, has kind of $1, $2, and then we see a detail line that tells us what is the actual $1, what's the actual $2, which PgDay statements does not have. Right, so if you want to know which customer was affected, which part was slow, this is kind of essential. And another example of why this kind of can be difficult to understand what a query truly is if you just look at PgDay statements. So this query here, this is how it would look like in PgDay statements, right? And we talked about ORM briefly earlier. So this is an ORM generated query, and it's a huge in list, which Rails likes to do. And so the actual query here, right, was this. So it wasn't just a single dollar like question mark. It was actually about I think 500 values, kind of doesn't stop, right? And so that's why it's important to really look at query samples, kind of look at log output. All right, other things to look at. So if you want to understand what is happening in database from a query perspective, PgStat database is a useful table. So you have just a simple transaction counter in there. If you look at that over time, you know how many transactions are being committed per second, right? Which you could kind of then calculate a TPS from that. You also have counters for all the rows being updated and all the rows being deleted, inserted, and so on. So if you're just trying to understand what is the activity on the database overall without going into queries, PgStat database is a very good place to start. All right, and then here the action item, right? So we look at the workload, now what do we do? So obviously optimizing indexes is important, right? And looking at explain, which we just learned about 2 sessions ago. Tuning Postgres, which we'll talk a bit more about. And then sometimes changing your queries, right? Sometimes it is just like you need to change how you use the database. The database itself can't really do better. All right, next big topic, right? So we kind of talked about query workload. Let's talk about index optimization. So the questions that I would ask myself when I think about index optimization, right? Should I add an index? Like, am I missing an index? Did I introduce a new feature that forgot to add an index? Do I need to run a re-index, right? I think a lot of people don't re-index their indexes, but over time, an index quality actually deteriorates, and so there's significant performance difference if you have a new index that's newly kind of generated across a set of data versus an index that has seen a lot of updates. And then sometimes also, should I remove an index, right? Or should I not add an index? In the sense that indexes are actually expensive. Indexes are not always good. You should not index everything. All right, should I add an index? So one thing you can look at, and this is not perfect, right? But it's one thing, just one place to start, is you can look at PgStat all tables. And you can look at, there's 2 counters in there. There's sequential scan counter and a sequential scan kind of tuples or rows counter. So you can understand how many sequential scans are happening on this table and how much data are they returning. And that's kind of helping you, understand which part of the workload do I focus on. You can also look at the index hit rate through that, right? So you can kind of say, how many of all the operations that are trying to get data from here, how many of them, what percentage of them are trying to get the data through an index versus trying to get it through a sequential scan? And sequential scan, by the way, for those who don't know, is essentially just reading the data sequentially from the table itself, right? So it's a very simple operation. It works well for some cases, but it does mean that you have to look at a lot of data. It produces a lot of I/O. And so one guideline you could set yourself, and this doesn't always apply, but it's a good starting point, is for the index hit rate, you kind of want to start at 95% for like large active tables, right? So you want to mostly use indexes for most of the operations. All right, then this is kind of where it gets tricky. So should I add an index for a specific query, right? And assume that maybe I'm trying to understand for particular parts of my workload, so I don't necessarily have the actual query text, but I do want to start optimizing specific queries. And so you would think that PgStat statements can help you there, but unfortunately it's not that useful for that because it's kind of a very high-level view on it. And so PgStat statements doesn't actually know which indexes get executed, right? It doesn't tell you that, or what plan is being executed. It doesn't have many details on kind of what the parameters are, and so you can't run and explain on it. So you're kind of lost in the dark here a bit. Now, that's kind of where we come back to auto-explain. So we talked about auto-explain briefly in the explain session earlier, and really auto-explain I haven't used it much, if I look back 2 years, I haven't used it much back then. In the last 2 years, I really started using it more actively and really trying to build better experience around auto-explain. Because I think that, for a lot of systems, that's where the actual good data is in terms of, actual specifics about what is going wrong in a system. And so auto-explain is a bit hard to read, though. So essentially, and we're kind of making it hard on ourselves intentionally. So auto-explain outputs the explain plan, right? In this case, it does it in JSON, because for machine-readable formats, JSON is certainly better than the text format. And it does that in the Postgres log. So it's a very, kind of lengthy output. Also be aware if you turn it on for everything, like if you essentially say log, auto-explain every query, it's going to cause a slowdown because it needs to output to the log. So don't do that. Just do it for certain thresholds, right? Now, what we kind of did with pgAnalyze actually recently is we said, let's visualize this. And pgAnalyze is not the only place you can visualize this. Earlier, we heard about PEV, which Dalibo now maintains. Explain-Depeche.com is a good tool as well. There's a lot of visual explain tools that essentially take this JSON output and make it much more readable for us so we can actually understand what's going on. And so here, what's interesting in the context of indexing, right, is, for example, we have a sequential scan, and that sequential scan has discarded about 50,000 rows and returned none, right? So it looked through all these rows, and none of them were actually useful to it. None of them kind of applied to the filter, but it still had to scan through them. And so those are the kind of things that when we see those, if we add an index, we can obviously optimize a lot. So a good guideline here is, right, you should create indexes when there's kind of frequent sequential scans on large tables. If you have a small table, Postgres is usually going to do a sequential scan, even if there are indexes. So if it's a very tiny table, Postgres actually thinks it's faster to just read the whole table because, navigating a B tree is more complex. And then this is really nice, and I haven't spent enough time with it yet myself, unfortunately, but I hope to soon. So Postgres 12 added a way to measure index creation progress. So let's say you realize you need an index, right? And you create the index. We can actually go and look at the table PgStat progress create index, and it will tell us which phase the index building is at and how much of the table it has already read as it's trying to build the index. And that's really, really nice for if I'm waiting for an index build to finish because my application is slow and I'm almost down essentially, and I just need this index for things to be fast again. All right, do I need to re-index? How many of you re-index your databases somewhat on a recurring schedule? Anybody here? Okay, 2 people, 3 people, 4 people, including Peter. Perfect. So re-index, right, would recreate the index. It, as of Postgres 12, I believe, also does it in a way that it, from a locking perspective, is much more efficient. The way to look at re-indexing is you can do a bunch of estimation queries. The best quality data here is an extension called PgStat tuple that's also part of Postgres contrib. It is slightly expensive to run this in a sense that you shouldn't run this always, but if you want good data, this is the best place to get it. And so we run this on a particular table, and it tells us a density of the index. And kind of a B tree starts out at about 90% density, and then it kind of, as you're updating, the density changes, and I believe it usually goes down. And so here an example, right? If we updated 50% of the rows in the table, the density drops from about 90% to about 45%. And depending on the index, it has different densities, right? So that means now it's much more expensive to navigate the index, and much more expensive to read the data. And similarly, you can see the index double in size as well. And so that's a good case where you could re-index. And so one thing to do here is, like, if you feel that the index density has dropped a lot, you could re-index concurrently for better performance. All right, should I remove an index? I think it's really important to remove indexes. So you should look at PgStat all indexes to understand if there are any index scans. Do it over time, ideally, right? Because sometimes index only gets used once a week for some cron job. There is a simple counter in there for index scans on that particular index. And you can kind of run a query for that, right? Kind of sort by the, what's kind of the number of scans, like how big is the index and how many scans does it get. And so here, for example, we can see probably, we should evaluate if this like log lines index, like the fifth in the line, only gets 2 scans, right? So is that really necessary? Can we avoid that? It's a very big index, probably expensive to update to. And then, simplest case is if there's really no index scans, then you should remove it. The one thing to watch out for is replicas, right? So if you have an index on a primary, you don't actually use it on a primary, but you do use it on a replica, then don't drop it because you might actually need it. And then, unused indexes make write slower. Like every time you insert, indexes need to be updated or update. And also vacuum obviously needs to go and actually clean up those indexes. And then here's one thing that I find, like, I didn't know in the beginning when I looked at how indexes work. And so indexes, you think an index scan is kind of very different from, a sequential scan, right? In the sense that it doesn't touch the table, it just goes to the index. And I think it's important to realize that there's different kinds of index scans, but all of them go to the table, right? So if Bitmap heap scans, Bitmap index scans, kind of makes sense, right? So it kind of does a heap scan explicitly. But the other two also go to the table. So both an index scan has to go to the table sometimes, and the index only scan, even though it says index only, also has to go to the table. And you can kind of look at these two counters here to see that, right? So you can look at the PgStat all tables counter for index to fetch to see what the bitmap heap scan is doing in terms of table data. And then the PgStat all indexes table to see what the index scans and index only scans are doing. And if you do an explain, you can see the kind of heap fetches, which means that kind of based on the visibility information, it had to verify if a row was still visible by going to the table. And so again, this could have performance impact, right? Because it actually needs to load more data than you thought it would have to. All right. So, query tags. So let's say we have this query here, right? And we look at this from a DBA perspective. It's sometimes hard to say where a query comes from. Like, if you have a complex application and you have maybe multiple applications accessing the same Postgres database, it gets very hard to understand where it comes from. And so I found it really useful to introduce what I would call a query tag. You could also call it a comment. But the point is it's structured, right? So instead of just having a comment, you actually have your application generate a comment. And the comment says where it's coming from. So this query here was in the PgAnalyze application. Actually, we can look at this more structurally, right? So this is application PgAnalyze, controller GraphQL, action GraphQL. This is Ruby, so it has a particular, kind of source line. An organization type RB has a particular request ID, right? So now I know where this query is coming from. And that's very, very useful if you're trying to understand what is making things slow, what is causing issues. If you use Rails, there is a gem called Marginalia, however you pronounce it correctly, that works with active record. SQL is better, I agree. There's similar ways to do this for SQL, right, and similar ways to do it for Django, where you just, every time a SQL statement gets generated by an ORM, you just attach that comment. Or if you write your own SQL, you could just add the comments yourself. But the point is tagging those queries in the application then helps you kind of find out where they're coming from. And really the point is, right, if you're looking at this not from a database perspective, from an application perspective, you should really, tag the queries in your app so that then you can look at your database and understand where they're coming from. All right, connection pooling, hopefully this is not news to you, but well, first of all, we can get data about connections from PGStat activity. I won't go into a lot of details here today, but PGStat activity has a lot of information about what's connected to Postgres right now. The simplest thing that I would always try to look at is what's the number of connections by the state that they're in, right? So in this case, for example, we're looking at an application that actually is probably fine, doesn't need a connection pooler. So we're seeing kind of, one snapshot here is there's like 3 active connections, there is 7 idle transactions, which is a bit concerning, but there's not too many idle connections. If you do see a high number of idle connections, usually that means that you should look into a connection pooler. But mostly measure this, store it somewhere, right? Have your Grafana set up, your Datadog, your PgAnalyze, whatever you try to use, right? Make sure that you have connection counters in there because they are important. And if you see a high number of idle connections, add that connection pooler. All right, workmem tuning. We talked about workmem earlier a little bit. So workmem is interesting because it's this fundamental trade-off between running out of memory and having queries kind of operations spilled to disk, right? So if you do a sort, for example, sort runs in memory or runs on disk, usually both. And so if you have a high workmem, it runs in memory, but that also means you're more likely to run out of memory. If you're low workmem, you're less likely to run out of memory, but it does mean that you have it spilled to disk, use I/O, and so on. One thing you could look at, PGStat database just counts the number of temporary bytes written, right? So you can kind of say in this database how many temporary files have I written. I can then break this down further by looking at PGStat statements, which actually tells me which queries have written those temporary files. I can also look at the log files, right? So log temp files is a setting. If you enable that, it just tells you every little temporary file that gets created. In this case, we have a huge CTE that allocated, let's see, about 50 megabytes of worth of kind of temporary file, which presumably exceeded the workmem on this database. And then, if a sort spills to disk, you should increase your workmem. That's kind of the usual guidance. However, if you do that too much, then you will run out of memory. So it's kind of a, don't use the default of 4 megabytes, but don't go like 4 gigabytes probably doesn't work, but don't go 400 megabytes, right? Probably go somewhere like double it, like go 4 megabytes, 8 megabytes, 16 megabytes, 100 megabytes maybe is a good, don't go above that without thinking about it. And then if you get a lot of out-of-memory errors, the way to fix them is to reduce workmem. All right, last kind of component up here in this corner, buffer cache hit ratio, which a lot of people really like, and I also like it, but I think there's some things to think about there. So let's look at how kind of Postgres works, and this is a very simplified version. So people in the room who really know how Postgres works, because they do a lot of hacking on it, please disregard all the simplifications. But essentially, if we read data from Postgres, right, it usually comes from a data directory. It goes through the operating system cache, which is not pictured. Then it goes through the buffer cache, and then it goes to the backend, which actually sends the data back to the client. Doesn't always apply, but for simplification, it does apply here. And so there's 2 kind of paths here, right? There's the path where we have the data in a buffer cache, so we don't need to go to disk, or we don't have the data in a buffer cache, and then we do need to go to disk. And we can measure this, right? So we can look at PGStat database, see this across the database. We can break it down again by going to PGStat statements, which tells us, which queries essentially had which cache hit ratio. And then we can actually calculate this as a percentage. So this is, again, something where a lot of people say that, it should be like 98 or 99% to have good performance. There's a couple of problems here, and other people could say more about this, but my understanding right now is that the hit, like shared blocks hit counter in particular, overcounts a lot, right? Because if you read the same block again, it also increases it. And so there's problems there with, how good is this number really? But generally, you don't want it to be very low. You'd want it to be in the high 90s. And then we can do the same thing on a per table basis. And this actually brings me to the next point. You should look at this over time, right? So you should look at this not just in the moment, but you should try to graph it, store it somehow. And then here, for example, we can see there were actually kind of, mostly it was 99.9%, but then it did actually drop down. And it's likely that then we saw kind of performance issues at that time, which might have been because another query needed the shared buffers. Also, PG buffer cache. So if you really want to know what Postgres is caching, PG buffer cache is also in Contrib. This is a kind of visualized table version of it, but essentially just tells you, what's in your buffer cache. So here, for example, we can say, 58% of the buffer cache is used by a table called schema columns, right? So 58% of the data in the buffer cache at that moment was used by that table, which means that, other things are probably not cached because this particular workload was exceeding the memory. And so, that's something where if you're wondering why do I, keep hitting the disk, keep hitting the operating system cache, this is useful to look at. And then Andres, who I think is somewhere here, had a really good tweet recently being September 30th, so I guess, last year. So shared buffers, right? There's a general guidance on saying 25% of shared buffers is good. And Andres did some benchmarking and concluded that in his particular benchmark, that was not the case. It was actually better to be either lower or higher. So just kind of a reminder that you should benchmark shared buffer settings because it does make a difference. And to 25%, that's the standard guidance, doesn't always hold correct. All right, and now let's say our workload doesn't fit in memory, right? What can we do, right? So we get kind of low buffer hit ratio. We kind of need to improve it. So we can either change our workload or add more memory, right? For the purpose of this, let's look at adding more memory. Obviously, scaling up is an option. I also want to call out scaling out, right? So using something like Citus, I think Timescale also has, kind of distributed partitioning now. But essentially anything that goes beyond a kind of single unit and a single server and allows you to scale out. All right, lock contention. And this is kind of the last of the group to query performance, and then we'll talk a bit about I/O. So lock contention is a tricky problem, and I'm still not happy with how difficult it is to understand, what really holds which locks in Postgres and what can you optimize about it. Like there's PG locks, which we'll talk about here, but it's not great. It's hard to use, as in you need to kind of sample it, and you only ever see a moment in time. So PG locks kind of just tells you which connection holds a lock at this point. That's a 10-minute mark, I believe. Excellent. So it tells us, which process holds which lock. It tells us if something is waiting for a lock or if, we kind of already have the lock. So you can see, what's being waited on. You can also see what's being held right now, which is, sometimes useful because oftentimes this tells you which locks are active. And then you can also use lock waits to kind of see it in the log. The thing I want to call out for the ORM users here is really watch out for how complex your transactions get, because when I usually see lock contention, it's because of complex transactions that people don't intentionally write. And here's an example from Rails. So Rails has a counter cache, which is kind of transactional and kind of safe to update a +1 essentially. And so what it does here, it's a begin, then it does a bunch of selects, it does an insert, does another select, then there's probably some, Ruby side changes that it's doing. Ruby is not always the fastest, right? So like, this is essentially something that takes multiple hundreds of milliseconds, maybe multiple seconds. All whilst, for example, the update, right? The update user set updated at here holds a lock on that row. And that's a pattern that Rails very often has. And that means that you will see lock contention around particular rows. All right. I/O. So I/O is important, as we all know. The advice earlier, by the way, for provision IOPS on EBS volumes is generally a good one. Unfortunately, it's very expensive, but it's usually a good idea. So, you could look at the system level I/O metrics, and I won't talk too much about them here, but just, that's a good starting point. Once we kind of, go into Postgres, what are the things that we always have available? So we always kind of know what data is being read from the disk or the OS cache. So we can kind of look at, database kind of blocks read. We can look at the heap blocks and index blocks read. And then in stat statements, again, we could also look at the shared blocks read. This is actually a somewhat useful counter. It doesn't tell you how long it took. So if it's really fast, it could be from the OS cache, but you don't see that here. The other thing to look at is transactions per second, which we talked about earlier. And then the thing that is really useful, and I would always, these days, turn it on modern hardware, is track I/O timing. Track I/O timing just measures how long an I/O operation takes, which means that we can then break down per database, for example, how long the I/O took for reads or writes, and then we can also do that in stat statements, right? So we can see how long each statement took for I/O. Now let's look back at our kind of, how Postgres works diagram. So backend kind of, writes something. It would write that to the wall. It would also write it to the buffer cache and data directory. And then, kind of can also sometimes write directly to the data directory without going through the buffer cache. The other thing to think about is, obviously we have the kind of the read path that we looked at earlier. And now there's kind of this important part of here where you need to get something into the buffer cache, so something else needs to go out of the buffer cache because there's no space, right? It's a limited buffer. And so that's why we'll briefly look at PgWriter and checkpointer here, both of which are important to kind of free the buffer cache so you have space for other things. Let's talk about checkpoints first. So checkpoints are kind of important for I/O tuning because they are very expensive. But you want them, like they're good for you, in a sense that they're good for recovery, right? If you're trying to recover your database, you kind of need a consistent point where you start from. That's where a checkpoint comes in. So the checkpointer is a process that always runs in the background. It kind of has the responsibility to essentially create these save points, restore points, where you can say, okay, from this point, my database is consistent. Now, the other role it has is it flushes the buffer cache, kind of the things in the buffer cache that are dirty, into the data directory, so that there's space for reuse again. Things to look at for checkpoints, right? So checkpoint starting is a very simple log event. You would almost not notice it, and that's 5 minutes, I believe. You would almost not notice it. But it outputs, very important detail, which is why did the checkpoint start? So here, it started because of xlog. Xlog meaning, kind of the wall. There was too much wall being generated to exceed the max wall size setting, and so the checkpoint has to happen right now, because we're essentially exceeding our allocated space for wall, which is not a good kind of checkpoint. The good checkpoints are checkpoint timeout based checkpoints, which are, says checkpoint starting time, which means that the checkpoint can be scheduled, can be kind of, done over time instead of doing it immediately. We can also graph this. So this particular database is not doing well in this regard. This particular database has a couple of time-based checkpoints, but this is over 24 hours, has 2,000 wall-based checkpoints, right, xlog-based checkpoints, which means that there will be a lot of kind of spiky I/O based on these checkpoints. You can also get this data from PgWriter, which kind of tells you just, two counters, like how many checkpoints happened and how many of them were timed. Usually the log is a bit easier to use. And then generally the guidance here is, right, if it's safe for you to do, increase the max wall size. But you could also consider reducing a checkpoint timeout and essentially saying, well, I know that I need to write a lot of data, right? I need to write to disk, so let me just, do it intentionally and more often. And then the other thing to look out for is checkpoint completion target, which says, if it is a time checkpoint, how fast does it write, right? And 0.9 is a good value, but not always. Like, you should, understand what it does and kind of when it hits the I/O impact. All right, background writer. So the background writer, this kind of brings us back to this topic of the buffer cache is limited, right? Like, it's not an infinitely scalable, variable length array. It's actually a fixed kind of size buffer that's allocated at start and that stays the same over the runtime of Postgres, which means that we really need to manage it and think about what's in there. So how do we get something out of the buffer cache that's kind of, data that's not written to disk yet? So the checkpointer can do this, right? Now, the important thing is the backend can do it as well. So if a backend is trying to load data and there's no space to essentially get things into the buffer cache, it first needs to flush things out to then be able to load things in. And then really the process that is supposed to be doing it or does it well is PgWriter. Checkpoints are also fine, right? But really what we're trying to avoid is having the backend do this kind of work here. And so we can look at PgWriter as a kind of table that tells us about who kind of flushes out this data, right? So if its buffer's clean is good, right? It's the PgWriter. If its buffer's checkpoint, it's the checkpointer. And if its buffer's backend, it was the backend. There's some processes in buffer's backend that are not necessarily bad, so don't be alarmed if this has a value, but it shouldn't be most of your workload, most likely, right? So there should, most of this should either be a checkpointer or the PgWriter. And then you can reduce kind of the PgWriter delay or play with max pages to kind of have more buffers written by the PgWriter to kind of shift the workload towards that PgWriter and not the backends. All right, last topic, and I think we're almost at time, if not at time. So let me go quick here. So auto vacuum, we talked about it earlier, but I think the talk was really good, so you should just rewatch it if you want to learn all the details. Quick recap, right? So auto vacuum, you see in PgStat activity what's running right now. You can graph that over time. So here, this is kind of a time series type view on the same data in PgStat activity. The thing that's really useful if you have a currently running vacuum is PgStat progress vacuum. That's the same as similar idea behind the create index kind of PgStat progress view. This tells us about a currently running vacuum. And then we can also graph this over time. This is useful because you understand, what is it trying to do? Like a vacuum is trying to first kind of scan the table, right? Find all the things that are dead that can be cleaned up. Then it needs to go to the indexes and clean up the indexes. And then finally it can clean up the table. And so if you have a lot of indexes, for example, right, you will have multiple vacuum index phases here as, it tries to clean up things. Versus if you have no indexes, then it would go really fast. So helpful to look at and understand, what is the workload in vacuum. And then this is two really quick tips here. If you reduce, so Postgres changed a default, and so it used to always be that Postgres reads data for vacuum at auto vacuum at 8 megabytes per second, which means essentially it was very slow, and it was so because historically that made sense. In Postgres 12, that was increased and was tenfold increased. It was done by reducing the cost delay, like essentially sleeping less often. Sleeping less often. Or sleeping at the same amount of time, but not sleeping as long. So not sleeping as long, and that essentially, 10x the speed it was reading. And that's generally, I think, a good setting. So on most older systems, you can increase the auto vacuum cost delay, decrease the auto vacuum cost delay to increase the throughput, and that will, make your auto vacuum go faster, which then, has benefits in terms of not getting to transaction ID wrap around, and so on. And then really use table partitioning. Just want to put it out there again. I don't think people are using it enough, and it really is a good feature, and it really helps you make vacuum be much less painful. All right, those are all the things that we looked at today. There's probably still another 50 metrics we could look at. We're not going to do it, but this is kind of what I think is important. Hopefully, it's useful. And then if you want to get the slides and learn more about Postgres, in particular what Citus and Microsoft are doing with Postgres, look at the Citus newsletter. We'll also tweet out the slides, and then this QR code also goes to the newsletter in case that's interesting to you. Great, thank you. Any questions? I have one question in the back.
I was wondering if you could explain why auto-explain adds latency and like the underlying reason it adds latency to queries.
Why auto-explain adds latency?
Yeah.
Great question. So the question was, why does auto-explain add latency to queries? Because I mentioned that earlier. There's actually a couple of ways how auto-explain can add latency, unfortunately. So auto-explain can do explain analyze, and if you turn on log timing, which by default is not turned on, but if you turn it on, you get the same output as a regular explain analyze, but it's actually expensive to do that. So that's one thing to watch out for, is don't turn on that setting. What I meant earlier was that if you have a lot of log output, the same holds true if you do log statement all, for example. That's actually expensive, right? Because Postgres then needs to write these logs to disk, and there is overhead in that. So essentially, the way I've seen work well is set a threshold like a second, like only actual flow queries, right? And then turn off log timing so that you don't have that problem with the overhead there.
So you're saying the latency comes from flushing the logs to disk rather than actually measuring the cost in Postgres?
Yes. And it's both, but yes, certainly the pure fact of writing a log line has overhead. Okay. In general, anything that does a lot of log output, I would be careful of. But again, if you tune auto-explain right, that doesn't happen, right? It's usually only the outliers that exceed it. Sure. Yeah, go ahead.
Very simple question. I'm new to this world, but the table or view that showed all the SQL statements that had happened with things about them, you had dollar notation in it. Were those corresponding to actual use of that in a prepare statement, or do ordinary literal values get transformed into that as well as part of what you call normalization? Which of the two?
Yes, great question. And so the question...
I'll just get the follow-up question and then you can answer.
Yes.
Does that view show you the stuff from stored procedures as well?
Yeah. So the question was like, when we looked at the query text, we had the $1, $2, right? Was that because it was a parameterized query, or was that because PgDay statements normalized it? So PgDay statements always normalizes. So it's always like the form, and there's some edge cases, but it should always normalize essentially. So it's intentionally not showing you the constants, like the actual values. It always tries to show you the normalized form, even if you didn't use a parameterized query. Is that?
Store procedures?
Well, store procedure is tricky. So you can set, if you have something that's running inside a store procedure, well, the same thing applies. So it wouldn't, like if you call the store procedure and you had a parameter to that procedure, it would also normalize that.
No, I meant the SQL out of a stored procedure.
The SQL in the store procedure?
Yeah, that issues.
Yes, so that's the same applies there. So that also gets normalized. You would also not see the query, the actual values that get run.
You do see the query.
You do see the queries if you turn on, there's a setting for it, but yes. There's a setting that says, do you want these like PgDay statements to track, and I think it's either top or all. If you set it to all, then
You have to be aggregating the offline level for that to make sense, because the whole point is you're bunching it all in together, all the constants, because that's what you decided to do. Let's say you're aggregating the cost at that level specifically, because presumably that's the most useful level to do that.
yeah.
You can have your query files just the same as query logs, right?
So I didn't catch it, Peter, but it also was a comment, right?
In terms of the different query files have the same query text, right? So you're by definition, those things get linked together. That's sort of the point. You could, in principle, have it aggregate at the query file level, but that would be a different thing, right?
And for context, also Peter wrote some of the normalization code, so Peter would be a good person to talk to if you want to know all the details. All right, other questions?
So you mentioned so there's the shared cache and there's also the data directory, and there's OS caching as well, right?
Yep.
And so at my company, we don't tune the shared buffer at all. We just use OS caching for everything. And I was wondering like if there's a performance difference from that.
So you don't tune the share just to, okay, so at your company, meaning which company, like your particular use case, or?
Yeah, I mean, I don't know if that's the best way to do it. It's just been historically how.
I mean, I would measure it, right? It's like so in general, none of this is, there's not one truth, right? Like the truth depends on what your workload is and how, like, what you've experienced yourself. I think generally people sometimes forget about the OS cache, right? So it's good that you're thinking about it. There is a double buffering effect, like the tweet that I referenced from Anders earlier, right? Like that there is a reason why that was fast kind of at the lower shared buffers, and it was slower because it was kind of a bad point in the curve, and then it was faster again. So in general, I would say maybe it makes sense for your workload, but I would certainly benchmark it, if that helps. Other questions? Are we in time? Are we, one more question, or are we? That's it. Cool, awesome, thank you everybody.